the official topic for the day, and later on we'll see how this matches up with the four-card problem. But it all comes down to the problem of showing whether one event causes another, cause and effect. So, for example, a person has a headache. They take a headache tablet, paracetamol. The headache goes away. It's a reasonable question to ask, did the tablet cure the headache, and will all tablets in future cure future headaches? Likewise, a non-clinical setting. The price of railway travel goes up. Then you get fewer people on the trains. Did the price increase cause that reduction in train numbers, or was there something else going on? Next question, will passenger numbers in future go down again when rail travel increases in price again in future? In other words, will these observations be consistent? Likewise, when you are treating patients, treat somebody, somebody gets better, will it happen that way again, or was it just coincidence, just luck, just a fluke, as it were? So it comes down to cause or coincidence. Things change regardless of what we do. Headaches, usually described as a self-limiting illness, they rarely last forever, they go away by themselves. There's also the placebo effect. The very act of taking a pill might lead you to expect the headache to go away, and that might be sufficient for you to perceive a reduction in symptoms. And it just so happens that train numbers vary over time. So what is the real reason for the change? Could it be other things happening at the same time that are bringing about the change? For example, was it the headache tablet, or was it a glass of water? What's a known cause of headaches? Dehydration. So the glass of water might have been the active treatment, or the relaxing lie down, which is enough to allow that tension just to ebb away. Or with the rail travel, some other event at the same time, such as going on school holidays, there's fewer people commuting to work, that could have made the passenger numbers decrease. Well, we have in clinical practice a treatment which we'll call X, and an outcome, a result, a health measure called Y. And there's the possibility that even though those two appear to go together, yes, the patient gets treated and then gets better, there's always a possibility that the patient was not assisted by the treatment, but something else was going on instead, which is related to both, a so-called Z variable, the third variable problem. So even though you observe a connection, a valid connection, an empirical connection between the treatment and the outcome, it might not have been the treatment which was doing the good work. Of course, it could have been the treatment. No one's saying that all treatments are ineffective. Of course, if that was the case, we might as well just close down the shop. But it's whether or not the treatment is always effective, or there could be some instances where an ineffective treatment can appear to be effective. So there's an unknown factor linking the treatment and the outcome. So the treatment appears to go with the clinical change, but in fact has nothing to do with it. So the clinician sees that health improves with treatment, and they make a causal inference. This is a psychological step, according to David Hume. It is we who conclude that the treatment had that beneficial effect. Now, that causal inference could be correct, but how can we be sure that it is correct? How can we know that what we're doing is really what's driving the observed improvement? There could be some unknown background factor. For example, someone goes on a diet and they lose weight. And so they say, well, that diet worked. What they're not accounting for is at the same time as they started the diet, they also began an exercise regime, and it was the exercise that made them lose weight. But they prefer to attribute the result to the diet. And this is happening all the time, these sorts of reasonings. Now, for example, just these last few days on the radio, I heard that a small family-run news agency at Taylor Square in the inner city has closed down after, I think it was, 80 years. And this closing, they weren't getting enough customers, they were losing money, so they closed after 80 years. So why did this happen? The blame was placed on the alcohol lockout laws. And the radio was saying, this is 100% due to the state government's lockout laws, which of course, as you would know, are expected to reduce street violence, and apparently the people who were the emergency doctors and the paramedics and the nurses at St Vincent's Hospital who get to clean up the mess and fix the broken bodies from all this street violence that was occurring. They're happy with these rules. They're making a causal inference as well. But back to the news agency, the radio was saying that we're 100% sure that this is because of the lockout laws, which of course leads them to conclude that the lockout laws are a bad thing. Well, how can you be sure that it really was the lockout laws? Now, I have no opinion on this personally, and they also said that there was an 84% reduction, an empirical fact apparently, an 84% reduction in pedestrian traffic, people walking past. Well, of course, that would reduce your customer numbers, and so the lockout laws are, in fact, a very plausible explanation for this. But have we proved from this one example that it was the lockout laws? Now, it just so happens, by the way, the story goes that if you want to make money, don't buy into a news agency at the moment. It is not a business of the future. News agencies have been doing very well over the decades, but their future is limited. The sorts of things that news agents sell, we are no longer buying. We're not buying as many newspapers as we were, and you can get them at supermarkets anyway. Greeting cards, not so popular. Magazines, not selling the way they used to because, of course, people are just using the internet. Pens and pencils and stationery, people using keyboards. Look at you all out there. I do see pens, but not as many. How many of you have ever bought writing paper just to write a letter? Decorative writing paper? No hands up, perhaps because you're quiet or because you've never bought it. And there's competition from the big superstores like Officeworks. Well, apparently they noticed a decline in business since 2012, but this could be other factors as well. Now, the other possibility is that both factors could be applicable here. It could be the lockout laws and the general decline in news agencies. Of course, the way you would test this out is to see how news agencies are performing outside of the areas that are affected by lockout laws, which could be your local suburb. In other words, have a control group, but more on that later. The point is that it is so easy and tempting to jump to conclusions, and you hear it a lot in the media, especially in political life. Something happens, the government's popularity goes up and down, before or after the budget, then the polls change, and these sorts of changes are attributed to events, but it's very hard to prove that those events were in fact the true cause. The technical issue was that of confounding, the so-called third variable problem seen on the previous slides, and it doesn't have to be just 3 variables, it could be 4, 5, 6 or any number of these unknown factors that are affecting the outcomes and also linked coincidentally with treatment, and those background variables can affect the validity, the truth of our causal inferences. Put technically by a book by Cook and Campbell in 1979, threats to the validity of inferences about putative causes and effects. You don't see that word putative often. I used to see it never. I first saw it in this book and then didn't see it for decades. I think I might have seen it once or twice in the last couple of years, so it's still a rare word, but it means supposed or believed to be true. And valid, of course, as you know, is true, trustworthy and well-founded. Well, this Cook and Campbell book, called Quasi-Experimentation, you'll see that word later in these slides, is, obviously it's an old book, and how often do we tell you don't quote anything more than 5 years old? Well, this is more than 5 years old, but it is a well-known book on this subject, one of the first major textbooks to address this in a lot of detail, at least one of the first that I know of. And if you go to the library, you'll find multiple copies of this book on the shelf. It's not the last book ever written about this, but it's certainly one of the more important. And in Cook and Campbell 1979, they refer to a learning motivation study involving this soft toy character, whom we can see here. Could somebody tell us, someone who could read, can someone tell us who this character, this yellow fellow, is? Big Bird, and from the children's television series known as Sesame Street, educational value, better than that cartoon junk. Anyway, The idea is, and you know, Sesame Street, if you've ever watched it, talks about numbers and letters and reading and all that stuff that children should know. The idea from the researchers back in the 1970s, Sesame Street's been around for a while, was, well, let's see whether Big Bird and other Sesame Street characters can encourage children to read. So let's take a sample of children, test their reading, put Big Bird in their houses, and then test their reading 6 months later. And lo and behold, what happened? The children's reading improved. So the researchers, as we are all tempted to do, made a causal inference that Big Bird alone, Big Bird soft toys, will improve children's reading. So let's hand out the Big Bird soft toys all round, every school child a Big Bird, and that will improve reading. Well, it is reasonable to ask as to whether that money spent on Big Bird soft toys is well spent. The question is, did Big Bird, and only Big Bird, improve the children's reading? Can anyone see a possible problem with this causal inference? Measuring children's reading, put Big Bird into the house, 6 months later, measure their reading again, and find the children's readings improved, so it must have been Big Bird. What's the problem? If there's a problem, or is it a valid causal inference? Have we proved that Big Bird is effective? Feel free to answer.
Children's reading life improves over time anyway.
Exactly. Every child is reading better 6 months later compared with 6 months before. So children just naturally, and because of teaching, they're also attending school, and perhaps their parents are reading to them as well, their reading improved over 6 months. Well, that's what you'd expect. So the idea that Big Bird alone is a sufficient explanation for this is obviously rather dodgy, but of course that's what the researchers preferred to believe, and so that's what they did believe. They jumped to the conclusion, and this obviously is scientifically kind of dodgy information, but nevertheless convinced the researchers. And Cook and Campbell, they thought this study was so important. Well, Cook et al. In 1975, they wrote an entire book about this very topic. Well, Big Bird was confounded, that is, matched up with other things going on that could easily affect children's reading. And to try and do something about these confounding problems, we have randomised controlled clinical trials, RCTs, that are at least designed to reduce or control or eliminate the effects of these confounders. And when you do that, the nice idea is that the treatment becomes the only reasonable explanation for the observed change, that you are safe in concluding that it was the treatment and only the treatment that caused the change. So the idea of the randomised controlled trial is to improve the validity of causal inferences about the putative effects of the treatment or intervention on patients' health. And the learning goals for this lecture, as you can see there, tied up with all of that, but you can read that for yourselves. You need to know a few big words. These words are taken from health and medical research in general. Keep reading and you'll discover them. So what the researcher or the clinician, both the same, clinical practice and research are the same thing as far as we're concerned here. What you do, or what the researcher does, is the treatment or the intervention could be a headache pill, exercise, change environmental exposure, stay out of the sun, or go out into the sun and see what happens to your complexion. That's the treatment or the intervention. But what is measured, the outcome or result, is what you're trying to change, usually some measure of patient's health. The occurrence of illness, whether the person's sick or not, or how severe it is, or for rehabilitation, some functional measure. Now, the amount of change in the outcome is called an effect. Also, if you like, a treatment, where there's a treatment going on, it's a treatment effect. So a change in how often the illness occurs, a change in the severity of the illness, or a change, for good or bad, in the patient's function, we can call that an effect. So an effect is a change which, if there's a treatment going on, can get blamed on the treatment, and we'll call it a treatment effect. More words. A variable a statistical term, but do not underestimate the influence of statistics on healthcare. The influence of statistics on healthcare is huge. Makes you wonder sometimes whether healthcare is run by statisticians. It's a scary thought. Anyway, a variable is anything measurable that can change or vary from one person to another. You are not all the same height. You don't all earn the same income. You're not all the same age. You don't have all the same eye colour, and so forth. So there's variation. So all of the things I just mentioned, height, income, eye colour and so forth, they are variables. Also, whether or not a treatment has occurred. A treatment can happen to some people and not others. Therefore, the treatment or no treatment becomes a variable. Now, the independent variable is whether or not the person has had the treatment. Yes, they have. No, they haven't. And that is a presumed cause, a putative cause. As a clinician or a researcher, you suspect that that treatment is going to influence the outcome. The independent variable is what you want to test the effect of. The dependent variable simply becomes the outcome, what it is you're trying to change, a measure of health which can vary, not only amongst people, but also across time. So a variable is not just something which different people differ from each other on, but can vary within the same person over time. And of course, in clinical practice, that's what you're trying to change. You're trying to change some sort of outcome measure over time. And that's what you're trying to affect. So we say that an experiment in research aims to find the effect of the independent variable on the dependent variable. So the effect of a headache pill, independent variable, on headache severity, dependent variable, the effect of exercise on physical fitness. So the word of goes with the independent variable and the word on goes with the dependent variable. That's an easier way to remember it. And of course, as a practitioner, you too want to know the effect of the treatment on the patient, on the patient's health measures. It just so happens, as we keep telling you, that just because two events go together does not mean that one causes the other. One of them might cause the other, but it is not guaranteed. It's not logically true. Again, read David Hume in the study notes, and there's more about that there. So two observations that occur in the same place at time, or just one slightly before the other, looks as if one causes the other, but it is evidence for causality, but it is not proof. So remember, the idea of causality, that one event causes another, that's effectively, at least according to David Hume, a psychological process. It's you, me, and everybody else who is making those judgments. So it's possible that the two events are causally related, one causes the other, but it could also be a coincidence. For example, suppose we observed that people who drink more also get lung cancer. Well, it's possible, I suppose it's possible, that drinking causes lung cancer, that alcohol causes lung cancer, but no one seriously argues that. There is a suspicion that alcohol causes other forms of cancer, but no one that I've heard of suggested lung cancer. But suppose we found that to be true in a statistical sense. There was a statistical association. It could be because the people who drink also smoke. So it's not the alcohol consumption, it's the tobacco consumption that goes with it. Likewise, we could say that young people send more text messages than older people. I don't know whether that's true or not, but supposing it was, then you might conclude that sending text messages makes a person younger. Goes together. Young people send more text messages, so send even more text messages and you'll never get old. Of course, that makes no sense. People don't get old because they stop sending text messages. So, but nevertheless, because, I mean, that's obviously a crazy example, but again, it's crazy, but it's easy to jump to these conclusions even for events that are not quite so crazy. So in non-experimental research, especially non-intervention research such as observational studies, more about those later, it's hard to be absolutely sure about cause and effect, you can still have pretty good evidence. No one's run a clinical trial that I know of testing the effect of sun exposure on melanoma. That's all observational evidence, and it's still pretty good evidence. Everybody believes it, but it's still not quite as good evidence as you might get from the randomised controlled trial that you could never run. And for a long time, the tobacco companies used to play on this one. They'd say, oh yes, but no one's ever run a clinical trial on smoking. We might have done it with rats because you're allowed to do that, but you can't set up a clinical trial with human beings on tobacco and seeing which ones get lung cancer, and so therefore we're relying on observational studies only, so the evidence is not so good. Well, technically they're right, but the observational evidence is so overwhelming, there's just so much out there that even though the perfect study has not been done, you're still running a risk by smoking. So you can get good evidence. Well, experimental evidence at best does improve the strength and the confidence that we may have in causal inferences by at least attempting to rule out as many alternative explanations for the observed effects as possible. There are also some causes, as I've hinted at before, that are logically plausible. For example, age is always a cause and never an effect. So hang around long enough and maybe on your 28th or 29th or 30th birthday, you're going to find a grey hair. And of course, that will be a very traumatic experience for you. Your first grey hair, it's nothing to celebrate. And so, of course, you're going to just rip it out straight away. But the trouble is, what's going to happen? You're going to get another one. And another one. You're going to be ripping out a lot of your hair. By the time you finish, you'll start to look like me. And they're still grey. You can't stop it. Well, in fact, there is a treatment that works. Just go down to the supermarket and buy yourself a bottle of coloured shampoo. But the point I'm getting at is that the grey hairs are appearing because you're getting older. You're not getting older because of the grey hairs. The grey hairs aren't making you young. Rip out the grey hairs and you won't stop having birthdays, if you get the idea. All right? Same with wrinkles. It's the age that gives you the wrinkles, it's not the wrinkles that make you old. You might notice that first wrinkle appearing with the grey hair. Yes, and you know you're on a slippery slope. Well, reasons to be cheerful or not cheerful. Anyway, back to scientific reasoning. Threats to inferences that X causes Y. X appears to cause Y, but it really doesn't. There's chains of events. X and Y co-vary. They go together in time and place, time and space. But does one of them cause the other? The possibility of third variables confounding. So X appears to influence Y, but only because of Z. For example, X causes Z, Z causes Y, so you can get these complex series of events occurring. For example, we might say that eating fatty foods causes heart attacks, but it does via cholesterol, which blocks the artery. So cholesterol is sort of the Z variable in the middle. Things can be complex. Or Z could cause X and Y. So X and Y appear to go together, as per previous slides. All of these events are called by Cook and Campbell history. That's their word for it. Things happening above and beyond the treatment that are influencing the outcome. So diet and weight loss, start a diet, lose weight, blame the diet, but really it was the exercise that you were doing at the same time. So back to this idea of bias, which you've heard before, including in foundations. There's a page, a table on the various biases in Hoffman. Also, the Cochrane collaboration, that publisher of systematic reviews, they want to know about bias and they want it reduced or eliminated from their systematic reviews. They have a whole section on these various biases. Now, a bias in general is a systematic tendency. It's a systematic effect. What do I mean by systematic? Predictable, repeatable, consistent. It keeps happening the same way. It's dependable. It's a distortion in measures or outcomes. It's a push in a particular direction. It is non-random. That's what makes it predictable and dependable and likely to keep happening in the same way in future. there's all sorts of biases, as you can see listed here. You can read most of them for yourselves. In fact, you can read all of them. Selection bias is concerned with sampling. How to avoid that? Use probability sampling methods, for example. And a way to reduce bias, not guaranteed, but a pretty good way to reduce biases. Not the only way, some biases don't work or can't be fixed this way, is to introduce random effects or chance which tend to be unbiased. So, for example, if you're selecting certain types of people who are not like the population, then use a probability sampling method to solve that problem. Allocation bias, this is where there are starting differences between the treatment and the control groups. More about this later, a lot more later, and that is solved by the randomised controlled trial. Now, the other biases there, detection bias, performance bias, attrition bias and so forth, and measurement bias, they can't be fixed using random methods, but you can read all that on the slide for yourselves. And more biases. Biases everywhere. Even the choice of topic. Some topics are popular and get researched, others aren't. That's a bias of sorts. Some research questions or some clinical questions never get answered, depending upon what the priorities are. Also, ethical restrictions on what can be done restrict the sorts of questions that get answered. Some populations are easier to research than others, so the easy to find people, they're the ones who are all researched, and that introduces a sampling bias. During the study, all sorts of things can happen. Attrition bias, certain sorts of people leave the study, and that biases the results. So supposing you're testing the effect of exercise on fitness, on morbidly obese people. Get a sample of morbidly obese people. Except the really, really, really unfit people, they find this exercise just so much work, too much sweat, they drop out, whereas the slightly fitter people, they stay on. They're the only ones with results. And so because they stayed on and the research and the exercise is more effective on them than it would have been on the people who left, then you can draw a biased conclusion from the results. Selective reporting bias, been mentioned before. I think that there's a bias in journal publications for statistically significant results, for results that tend to show that the treatment works, as opposed to the treatment not working. Non-statistically significant results tend not to get published, which biases the appearance of evidence in the research literature, biased towards statistically significant results. Also, results that tell people what they want to hear, as opposed to the truth. And also, even who's publishing. All these sorts of biases, however, these are social problems, generally rather than scientific problems, even if they're still biases, and experimental research and randomised controlled trials do nothing to prevent these sorts of biases. They happen outside the experimental design. Statistical regression to the mean. Slightly complex topic, and we'll dwell on it a little. And this is where an observed treatment effect is fully explained through a statistical effect. And I must say here that we have experience in asking students exam questions on various topics, and the topic, we have statistical evidence for this year after year, the questions that the students find hardest, the questions that the students tend to get wrong more than the others, are those about statistical regression to the mean. I suspect this is the hardest topic. This next slide is the hardest topic in the unit, judging by people's exam answers. We try to make the questions easier. In fact, the questions are fair. It's just that students don't get it. So let's see if we can get it. It's concerned with the fact that observations and behaviours and health experiences change naturally and randomly. We all have good days and bad days. Sometimes you feel just a little bit better than others. And perhaps you've woken up in the morning and felt a bit crook, weren't feeling very well, And so you think, oh, will I go to work or will I go to university or not? I'm just sort of borderline and I don't want to go all the way into work and then have to go home halfway through or start feeling sick at university. No. So you're undecided and then you feel a little bit worse and you think, that's it, I'll phone in, I'm sick. And then a half an hour later, you bounce back a little and you realise, oh, well, I could have got in anyway and it would have been all right. And later on the day, you're feeling better still, but too late, you've already gone to the shops. Too late to go back to work. But what's happening is you are observing natural variation in your own feelings and they move up and down for no particular reason. Well, the trouble is that these natural variations can be all too easily blamed on other things going on when the other things going on have no effect. Let's look at a classic example. This is like a story. I'm not saying this is backed up by research, but let's just think of this scenario where you have a champion tennis player, an elite athlete, who's practicing on court for the big tournament and the coach is sitting at the sidelines observing what is going on. And of course the coach is giving feedback to the tennis player, commenting on performance. Well, all tennis players, no matter how good, will occasionally serve double faults. There is natural variation in performance. No one is universally good. You don't get the same marks over and over again for all of your assignments. Even if you did the same assignment twice, you could get variation in your own performance. And likewise, the markers could vary a little randomly as well. Well, supposing the tennis player serves a string of double faults while practicing the serve. What's the coach going to say to the tennis player? They're going to say something positive like, well done, or might they say something slightly negative? Slightly negative, yes. Something along the lines of, you idiot, or, you silly Billy or something. Anyway, the coach has reacted to an accidental series of double faults which in no way reflect on the tennis player's usual performance. It's just a bit of bad luck which happens once in a while. And what happens next is that the tennis player keeps trying and starts serving the balls back into the square. Now, the coach has made a negative remark, and of course, like all of us, the coach likes to think that they're influencing things. We all like to think that we're effective. So the coach observes poor performance, says something negative. Performance goes back to normal, and the coach has made no difference. But what is the coach going to conclude? Poor performance, say something bad, better performance. What could the coach conclude? That criticism works. Yes, that saying negative things works. Now let's suppose that later on the tennis player works serving fantastically well. 300 kilometre an hour serve, smack into the middle of the service square. So hard and fast that the hole gets dug into the service square. This is the sort of tennis that you want to see. And of course the coach is going to say, what is the coach going to say when that appears? The ball is smoking. What's the coach going to say when that happens? Breaking the sound barrier. Oh, good work. Yes, fantastic. Let's improve your sponsorship. More dollars. And then what happens? Remember, the coach is ineffective. Nothing the coach says has any effect. What's going to happen next? Remember, we're talking about natural variation in performance. Unusually good serves followed by dropping down to normal performance. What is the coach going to observe? What is the coach going to conclude about the effect of positive comments? Yeah, it decreases performance. So you say something nasty and performance improves. Then you say something nice and performance gets worse. The coach is being trained to be negative, being trained by randomness. So anyone who's parented would know that children's performance or their behaviour randomly varies. So your children are rolling around the floor, fighting, throwing at each other, climbing up the curtains. You intervene, you say something negative. I'm just going to dump you at the Department of Community Services. I'm going to put you out to fostering or something like that. You know, should never have been born. Must be your father's genes or something, not mine. And later, shortly afterwards, because no child is extremely bad forever, the children then get out their homework, and you're going to conclude, oh, well, you know, telling off the children, that works. And then you say, oh, very good, you're doing your homework, and next thing you turn your back and they're mucking around again. You're going to conclude that positive commentary doesn't work and negative commentary does. But all you're doing is being fooled by randomness. So statistical regression to the mean is where we observe unusually extreme events that go back to normal, either very low performance or very high performance, going back to normal, and we think that the intervention that occurred at the time has actually done something when it hasn't. So this can happen when cases are selected for treatment purely on the basis of unusually extreme performance. And remember, patients seek treatment because they're at a low point. And it could be an accidentally low point. You treat them and then they improve. You think it's you, but they would have got better anyway. Just looking at the time, we do have just a little bit of time to explore this in some detail. This is a slide that you don't have. And the reason you don't have it is because you'll never see this in an exam. This is done using two random variables that are entirely computer generated. There is no real patient here. I said to the computer, give me two measures. I want both of them to have an average of 50 and a standard deviation of 10. Here they're graphed. With graphs, we want to know the big picture only. So you can see that the graphs there, by the way, they run, there's the average of 50, which is about halfway across. They're normally distributed, bell-shaped curve. Extremes are unusual, and this is the number of people vertically, and you can see most of the people are centred around 50. And here, there is 1,000, a large sample of 1,000 people, not real people, just 1,000 numbers, pretend that they're people, and each of them had been measured twice. Now, we can just arbitrarily label those two variables before and after, before treatment and after treatment. And as it happens, the mean is close to 50 and the standard deviation is 10, or very close to it. Even with random effects, you can get tiny differences from what you would expect. Okay, those are the two variables separately. And for those of you with binoculars, here are the last 50 cases, one per row, and you can see there's a bunch of random numbers there. Some of them are above average and some of them below average. For random number 1, the before. Random 2 is the after measure, and there I've got the different scores on the right, and you can see the numbers are all over the place. Next, because these are random numbers only, they are unpredictable from each other. There is no way you can predict the after score from the before score. How can we tell from this graph? Here are the before scores horizontally. For any score from left to right on the graph, looking up and down, the after score, the second variable, could be anything, high or low. Likewise, looking high or low on after, the before score could be anything. This graph is called a scatter plot. You'll see some more of them before you're finished, but because you've got that haze, that cloud of data points where every point is one score, sorry, one observation, one person, so to speak. There's 1,000 dots on that graph. Their score on both variables, you can see that the scores are all over the place and you cannot predict one score from another. So, for example, if the before score is 60, then the after scores could be anything from 30 through to, well, could be around 80 or so. Could be anything. Next graph. This time, on the next graph, I have the before scores on the bottom, but instead of having the after scores vertically, I now have the differences. I'm graphing before against change. And this time there is a definite relationship occurring. The graph slopes downwards from left to right. And here we have, in the middle of the vertical, we have 0, no change. Now the blue circles on the left are for the people, let's call them people, who scored below average on the before score. In other words, their performance was accidentally low. And what happens? Most of them have improved. On average, they improved by 7.55. On the other hand, the scores that were above average on the first score have mostly gone down. You can see that most of them are below 0. So the worse you were on the first score, the more you improved on the second score. The better you were on the first score, the more you got worse on the second score. And the difference between these is about 14 or 15. There's an effect here of about a difference of about 14 or 15 between the two average. This could be a treatment effect. If you selected the people for a treatment that doesn't work, a completely ineffective treatment, if you selected those people for treatment, then their scores would go up. But if you decided not to treat the people who were performing well because they didn't need treatment, you would find their scores had gone down. So you would conclude that this treatment was very effective, that people get better with it and people get better without it. And of course you are being completely fooled by random numbers. There is nothing happening at all. Well, there's plenty happening. There's a certain effect, but there's nothing concerned with any outside influence. That effect is entirely attributed to randomness. It's just the luck of the draw. It's the way the numbers work out. There's a statistically significant change. Difference here, p is less than 0.0001. It's not a chance effect, but it's the result of random numbers. Ways to kid yourself that things are working. Let's find out about pre-experimental designs. These are intervention studies. This is where researchers do what clinicians do. They treat people. They do something. But the design is classed not as a true experiment. They're easy to do, so they're out there in the literature, but the problem with these so-called pre-experimental designs is that they provide only fairly weak support for causal inferences because other possible explanations are difficult to rule out. You can't be sure of what's doing the causing. And on the NHMRC hierarchy, which of course you might recall from foundations, these designs are low-level evidence, at best level 4. Well, single-group pre-test only design. On an earlier set of slides which I put out earlier in the week, this was called the one-shot pre-test only design. I've just changed the labelling there to make that more informative. Have one group of participants, treat them and measure the outcome. Diagram there, treatment X, followed by an observation of the outcome. The treatment happens before the outcome. So treat somebody, measure them, and find that their measurements are okay, then you would conclude that the treatment has worked. Major problems. First of all, because there's only one measurement, the after measurement, it's impossible, logically impossible, to detect any change. You can't measure improvement by measuring people once. There's only one way to discover an effect, a change, and that's to measure people at least twice. So there's no way of knowing whether the treatment caused any improvement because you can't even measure improvement. It's that basic. So there's no way that if the person's performance is good, you can say that's because of the treatment. This study design is so bad that it doesn't even rate a level on the NHMRC level of evidence. It's not even level 4, and there is no level 5. So if you hear this kind of report, I treated somebody and then they were okay, if that's all you're hearing, then you need to be really cautious about accepting the effectiveness of that treatment. One group, pre-test, post-test design. Same as the previous, except this time the people are measured before and after treatment. So, for example, you want to know about the effect of caffeine on memory. You've heard about students drinking energy drinks, Red Bull and all those high caffeine and stimulant drinks to improve their memory. Well, let's do a test. Let's give them a memory test. Then give them some caffeinated beverage to drink. And then test their memory again. The good thing about this design is that you can detect change because there's 2 measurements. So you can get a treatment effect from this. But the disadvantage is that because everybody got treated, you don't know what would have happened without treatment. You've only got half the story. They might have improved anyway. This is not a marvellous design, and it's on the NHMRC hierarchy class as level 4, only a case series. So it's low level of evidence, but it's better than what was on the previous slide, where you only had 1 measurement. So some threats to causal inferences with these designs. Maturation, natural change over time. Okay, memory doesn't change overnight very well, so maybe that's not a great explanation for the caffeine study, the hypothetical caffeine study, but certainly over 6 months, children's reading will change. So the Big Bird study, which was a case series, has problems for that reason. Testing. We haven't mentioned this before, but there's always the possibility that the first test itself works like a treatment. People get better with practice. And if there's a performance component to that first test, like a skill, then it could be that the first test alone is enough to affect the results on the second test. For example, if we gave you a maths test and then gave you another maths test, the second maths test could show a practice effect from the previous maths test. You could get an improvement without any teaching between the 2 tests. Mortality, attrition bias, mentioned before. This is where certain types of people leave the study, and because those certain types of people would have given results in a certain direction, that introduces a bias. Instrumentation. If different methods are used, different techniques are used, or different tests are used for the 2 performance measures, that would introduce a bias. And if people were selected for treatment on the basis of extreme measurements, let's say extremely poor performance, they might bounce back naturally. That could be mistaken for a genuine treatment effect, so statistical regression to the mean is a threat to conclusions from the case series design. So how do we know that a treatment really works? The problem is we've got 2 observations with a treatment in the middle. You can get an apparent treatment effect even with an ineffective treatment, and there was a list of ways that could occur in the previous slide, and we don't know from the case series what would happen if no treatment was given, so the answer to that is to include a control group who does not get treated. So that way your experiment has a with treatment component and a without treatment component. So what happens without treatment? Sure, people might get better with treatment, but was the treatment necessary? The only way to find out whether people improve, or the only way to find out that the treatment is necessary, is to find out what happens without it. Which brings us to experimental designs, which have 2 groups. In an attempt to rule out other explanations for treatment effects that we observe, introduce a second group, a control group that doesn't receive treatment, and that second group could receive a treatment such as a placebo, a fake treatment that has no active ingredient, no reason to work, That's a control method of sorts, or some sort of alternative, some sorts of comparison. So that's testing whether the treatment causes a change in the outcome measure. That's the whole idea. And that causal inference nevertheless remains an inference. So the idea is that the experimental design has the two groups, a treatment and a no treatment or placebo group. And these are level 2 or level 3 on the NHMRC hierarchy. So the quasi-experiment, common in field settings, meaning non-laboratory settings, out there in the big wide world and applied research, NHMRC levels to level 3.1 or 3.2, or the pseudo-randomised or the non-randomised controlled trial, not a randomised controlled trial. Only if the treatment and the control groups are measured at the same time. If they're not measured at the same time, it becomes level 3.3 evidence. But here's the setup. You have an experimental group, measure them, treat them, and measure them again. You have a control group, measure them, don't treat them, and then measure them again. The treatment effect, the way to calculate the treatment effect is given for you on that slide, where you take the amount of change for each group, post-test minus pre-test for the experimental group, the treatment group, post-test minus pre-test for the control group, and compare those two changes. The difference in the changes for the two group is a single number measure of treatment effect for an experimental design, including the quasi-experiment as shown here. Well, let's run a quasi-experiment in our minds. Does junk food advertising affect obesity? Well, allow junk food advertising in Sydney and ban junk food advertising in Perth. Then compare obesity rates in the two cities before and after the junk food ban or no ban. And if you find that obesity rates diminish in the city where junk food advertising was banned, make the causal inference that banning junk food helps people to lose weight. Here's another example. In the workplace, does training work measure people's performance? Train one group of volunteers, then measure their performance before and after and compare the change in performance with people who were not trained, a control group that was not trained. And of course, if the trained group improves more, then you would conclude that training works. However, the problem is, with the quasi-experiment, that it's possible for the two groups to be unequal at the start of the study, and those starting differences in the two groups could be enough to account for a difference at the end. So it's not the treatment that's making the difference, it's the starting difference that was making the difference. So there's a false conclusion that the treatment works when the end point differences happened because of the starting differences. You can partly control for that with the pre-test, because the pre-test enables you to identify those starting differences, and there are statistical methods of dealing with that, but it's still not great. The problem is you've got non-equivalent groups. Now, in a running race in athletics, we expect the athletes, before the starting gun is fired, to be the same distance from the finishing post. That's what you would like. And you'd like that also with an experiment, that it's equal at the beginning in order to make it a fair test. Well, let's go back to our staff training example. Does staff training work? So you have a treatment and control groups, two groups. You've got the staff who volunteer to receive training, they're the treatment group, and the staff who don't volunteer and they don't receive training. There's biased allocation to the two groups. Different sorts of employees are getting training compared with no training. Well, they're not equivalent at the outset. Because they were volunteers, we could say that the treatment group staff who volunteered, they were just lazy people. They just wanted a day off work and a free lunch at some inner city training place, have an easy day. And they didn't pay any attention to the training. The people who didn't volunteer, they were really dedicated to start. They said, look, we haven't got time for these sort of free lunches. We have to get busy on it. We've got important work to do at work. And so they miss out on the training by staying at work. But had they gone to the training, they would have benefited a lot. The training program appears not to work. In fact, the training would have been effective, but because you were working only with lazy people, you got no result. And this is deliberately chosen, this example, because it could work both ways. These biases can make an effective treatment appear not to work, or an ineffective treatment can appear as if it does work. There are two ways of making false conclusions. The treatment doesn't work when it does, or probably it should do, or it does work when it doesn't. The solution to this problem is the full experiment, the randomised controlled trial, NHMRC Level 2 evidence. And this involves random allocation. You've got both observations before and after treatment and control. The difference between the randomised controlled trial and the quasi-experiment, Level 2 and Level 3 evidence, is the random allocation using a chance process to decide who gets put into which group. Drawing numbers out of a hat, random number generator, there's various ways of doing it. And here's the logic behind it. As we've heard before, people vary naturally in their performance. And those background factors, starting differences, could affect outcomes. And they might affect how the treatment also affects the outcomes. You don't want those starting differences to influence the results. The only thing you want to have control over the results, to influence the results, is the treatment. Random allocation assigns people to the treatment and control groups using a chance process. That means that any differences between the two groups at the beginning will be chance differences. If you have a large enough sample, random processes tend to give rise to small, unbiased effects. So with a large enough sample, it's likely that any starting differences will be small and too small to influence the outcome. Therefore, the only reasonable explanation for observed differences after the treatment or control has occurred is the fact that one group was treated and the other group was not treated. So by making the two groups equivalent at the start of the experiment on all possible variables, measured and unmeasured, it becomes a fair test of the treatment. So you get support for causal inferences, better support for causal inferences using RCTs, although within limits. The control group tells you what would have happened without treatment. And the treatment group tells you what would happen with treatment. Random allocation equalises the two groups. Therefore, the only difference between the two groups is whether or not they were treated, and the treatment becomes the only explanation for any observed treatment effect. Therefore, the causal inference is more likely to be valid. And for those of you who've read the study notes, and do remember the study notes are examinable in next week's quiz, there's a link between randomised controlled trials and John Stuart Mill's rules for causality. Remember, Mills said that A causes B if B happens if and only if A happens. That is, A gives rise to B if B is fully dependent on A. Well, the treatment group, if they get better, it shows that the treatment is sufficient. All you have to do is treat people, and they'll get better. You don't have to do anything else. The control group, who don't change, showed that the treatment is necessary, that people won't get better without the treatment. Those two events, together in the same experiment, effectively lock it in as far as the causal inference is concerned. You must have the treatment or patients won't improve, that's the control group, but if you treat them, they will improve, that's the treatment group. Therefore, the logic matches Mill. So, internal and external validity of a study. Don't get confused between internal and external validity of a study with measurement validity, as in the measurement study notes, which is a separate topic. Also important for validity, but a different style of validity. Now, internal validity refers to whether the conclusions of that study are true for that study. Never mind anywhere else or anybody else, whether the causal inference rather, is valid for that study. If it's poorly designed research, done badly, even with invalid measurements, then the results for the study are invalid. It's bad science. On the other hand, a study could be well done, but for various reasons, its results do not apply beyond the study. And of course, that's worth knowing for evidence-based practice, where you will not be working with the participants of a research study. So external validity is about whether those results will generalise or apply beyond that study. And of course, for evidence-based practice, you want both. You want the results for the study to be true, internally valid, and you want the results of that study to apply to the people you work with in the real world. Well, a randomised controlled trial protects against a lot of threats to internal validity. For example, biased allocation. Because the allocation is a chance process, it is unbiased. And because the two groups are equal, sometimes you don't even need the pretest because you know they'd be equal on the pretest anyway. A post-test might be all you need. Statistical regression effects will occur equally with both groups. So you can compensate for those, they are no longer a problem. Any differences in history or maturation that were occurring before the study started, any differences in background events before the study, that's most, not all, confounding problems, third variable problems, because they should affect both groups equally. Patient characteristics are the same on average for both groups. I'm not saying they're all the same. Not everybody's identical twins or anything. But on average, they'll be the same, and therefore it's a way of ironing out those differences, because there are no differences. But nothing's perfect. There are internal validity threats for which a randomised controlled trial does not protect against. And those are validity threats which occur after the study has started. Biases can occur, affecting the groups differently after the study has started, and randomised trials offer no protection against these problems. Unplanned, unknown or uncontrolled differences arising beyond the treatment and control group during the experiment and affecting the outcome. So mortality. So if mortality, like patient attrition, occurs unequally between different groups, you get different sorts of people leaving one group and not the other, that would introduce a bias which could affect your results above and beyond the treatment. It's not the differences in the treatment and control, it's the differences in the type of people who remain in the experiment that are driving the observed effect. If the researchers can't even do their statistics correctly, biased statistics, then randomised control trials can't save you. Other things can go wrong. Subversion of the treatment regime. Things don't go according to plan. For example, the control group know that they're in the control group and they go off down the road and get some treatment of their own. And the researchers don't know, which means they're not really a control group. That can mess up the results. Or compensatory rivalry. The control group, again, they realise they're the control group and they say, well, we're going to try extra hard to bend over and touch our toes on the functional measure of performance and back flexibility, if you like, because they know they're missing out on treatment, so they want to perform even harder. Or resentful demoralisation. These are all from Cook and Campbell. The control group goes on strike. They resent the fact that they're not getting treatment, and so they try less than extra hard on the performance measure because they know they're missing out on a favourable treatment. All of these things can occur after the experiment's begun. External validity threats that random allocation doesn't protect against. Well, frankly, it's all of them. Randomised controlled trials offer no protection whatsoever against any threat to external validity. External validity remains a possible problem. The artificial nature of many experiments, the laboratory problem. Well, yes, with the people in white coats in the wet lab, that's very different from your area of practice, not like the real world, and so results do not apply beyond the laboratory. Treatment interference. The way things are done in research may not be done the same way that you do them. Treatment in the big wide world can be contaminated, can be interfered with by other things going on. The way experimenters interact with patients could affect results in ways that don't happen in clinical practice. Blinding, more about that later, does attempt to compensate for that, but blinding is not always possible. More threats, external validity threats, pre-test sensitisation. In the real world, there might be no pre-test. Whereas in the world of research, things can be strictly done where there's more measurement going on, and so people are aware of how they're going to get measured, more aware, and that could affect their performance. That's, as I mentioned earlier, is an example of how a measurement itself, an assessment itself, could be seen as an intervention. Sampling biases. If the studies are done using the wrong sort of people, they're not going to apply to your sorts of patients. And volunteers are a particular problem here because people who volunteer could be different for people who don't volunteer for research, and that can distort the results. So random allocation offers no protection against external validity threats, but there is a sort of indirect protection from random allocation because it helps to preserve internal validity. And you'd like to think that higher internal validity assists, but does not, at least doesn't guarantee, but at least assists external validity. You can't expect invalid results to generalise to the real world. Reactive arrangements, this comes from the so-called Hawthorne studies. Well, some sorts come from the Hawthorne studies conducted earlier in the 20th century at a manufacturing plant. This was industrial research. They were looking at productivity and the workplace environment. And they found that by changing aspects of the workplace environment, people's productivity improved. For example, improve the lighting and people work better. But then they changed it back and people continued to work even better. Well, you might just think that people will just work faster and faster if you keep flicking the lights on and off. Well, it's a bit more complicated than that. But the general idea is that merely the act of observation and not the treatment itself, merely the fact of participating and being observed can be sufficient to induce a change in performance. So is it fair to say that when you got your P-plates for your driving test, you were much more vigilant, you were much more careful, you were concentrating so much harder with that driving assessor sitting next to you in the car than you might have been after you got your P-plates and you drove home telling everybody on your mobile phone while you were driving how you've just suddenly got your Ps, which of course you would not have dared do during the driving test. You weren't texting people saying, hey, I'm doing my driving test. You might not have got your licence. So the idea that you know that you're being studied can be sufficient to alter performance. That's not of scientific interest for clinical practice, but it can happen. So the workers reacted to the increased attention of simply being studied, which of course is a threat to external validity, because people aren't participating in research when they get normal sorts of treatment. Is it fair to say that, well, this has never happened to me, but participating in television's rating surveys where you get a black box which is sending off information about the programs you're watching, are you going to stop watching Sesame Street quite so often when it's being recorded and sent off to the market researchers? Your television viewing habits are being measured, whereas when you're not being measured, then you'll watch what you like. In other words, do you modify your behaviour simply when you are being observed? Rosenthal effects are another type of reactive arrangement whereby people change their behaviour in accordance with expectations as to what would happen. Particular problem in control studies with placebo groups. Imagine a trial where you've got the real drug and the sugar-coated pill, and the person giving out the tablets in the little brown bottles says to the treatment group with the real drug, well, these should make you better. Well, the control group, who get identical looking tablets, the researcher handing out the placebo tablet says, well, here's your fake tablet, lots of luck. And of course, those expectations will come through to the patient, which might affect their entire response. Blinding is a way of dealing with the way expectations could bias results. If people know what group they're in, when I say people, I mean that is patients or people working with patients, that could lead to certain expectations which affect how people respond. Single blinding conceals group allocation to the participants, so the participants don't know what group they're in. The people working with them and measuring them might, but with single blinding, only the participants don't know. On the other hand, double blinding blinds not only the participants to group allocation, but also the people working with them. And that way, the people doing the measurements, the assessments, or handing out the treatments don't know whether it's a true treatment or a placebo treatment. Of course, blinding is not always possible. You can't tell a physiotherapist that they're not really doing physiotherapy, that they're just doing some control condition. And likewise, you can't convince a patient that they're not doing exercise when they are, or that they haven't changed their diet when they have. So blinding is only practical where the treatment type can be concealed from either the people doing the treatment or participating, but ideally it should be concealed from the people doing the measuring to the extent possible. But of course, if it's a self-report study, if the participants are doing their own measuring and they know what group they're in, then there's no blinding, and that might bias their results. It's important to remember that random allocation should not be confused with random selection. Random selection is a sampling process. It's about getting people into the study in the first place. Random allocation attempts, random selection as a sampling process attempts to reduce or eliminate biases occurring between the people participating in the research and those in the real world to make sure that the sample is representative. That protects against external validity threats. Random selection protects external validity. On the other hand, random allocation tries to equalise the two groups. That protects against internal validity. So random selection attempts to equalise the research participants with the population. Random allocation attempts to equalise the participants in the two groups, thereby protecting internal validity. And in the real world of research, it's difficult enough to randomly select, especially when you're working with volunteers, so there's always a possibility of bias and external validity problems, and even random allocation is not always possible, just for practical reasons. So here are some conclusions about experimental designs. We're wrapping up. Experimental designs give stronger support, but not perfect support for causal inferences. You can never be sure, but you can be fairly sure, but never absolutely certain. Even the best randomised controlled trials don't prove that the treatment will work in all cases. But at least it's better than a non-experimental design or an observational study. But double-blinded randomised controlled trials, even though they're the ideal, not always practical. There's a lot of things that the researcher can't control, which rules out experimental studies or even intervention studies. Control groups could be unethical. It's never going to happen in a trial of a new cancer drug where half of the patients are randomly allocated to the control group and cancer treatment is withheld. Sorry, you're in the control group, we're just going to let your cancer kill you, naturally. That's the price of science. No, what do you think would happen? What can you imagine happening in a cancer trial of a new drug, where the new drug is the treatment group? What would the control group get? They get the alternative treatment, or they get the old drug. They get usual care, traditional care, what's worked in the past. And so the comparison would be, how much better does the new drug work than the old drug? Nor can you test using randomised controlled trials, intervention studies, toxic effects on people. You can't ethically run randomised controlled trials on sunbeds for melanoma, smoking for cancer. The story is now apparently 3 coal workers in Queensland have been diagnosed with black lung, which is an old disease formerly associated with coal miners. Long time to occur, but coal miners used to get it from breathing in all that coal dust. They thought they had that controlled with breathing apparatus and the like, but 3 miners have been diagnosed. Well, that doesn't prove they got it from coal mining. Funny thing is, though, that the 3 guys who got it were working in coal mining when everybody else in Queensland who doesn't work in coal mining is not getting black lung, so, you know, certainly the suspicion is there. But you can't run a randomised controlled trial on people to test that out, nor can you test death cap mushrooms on people, as we saw earlier. So sometimes you just have to use an observational study where natural exposure becomes the treatment. You can't always conceal allocation through blinding, and you can't always randomly allocate. So if you can't use the ideal, the researchers and you, the readers, need to be aware of the limitations of the weaker designs. And here's a slide which I threw in last night. If you've just got the study, if you've just got the slides today, this will be here. Earlier in the week it won't be. This is summing up why we do experimental research. You see that the patient improves. Fair enough, it often happens. The question is why? It could be that the treatment is effective. There's always a possibility that you're doing good. But there's always other possibilities as well. Body heals itself. Patients going off and getting some other intervention. Measurement error. Reactive effects and expectations. Regression to the mean. The patient saw you because they were feeling unusually bad. You don't know what would have happened without the treatment. All of these influences are hard to control in clinical practice. But researchers at least attempt to control them. Try to isolate the real treatment from what else is going on. The randomised controlled trial compares with and without for the same sorts of people. If you get a representative sample, that helps external validity. Blinding can help reduce the effect of expectations. And in research, they take special care to ensure that measurements are reliable and valid, so you're getting a good signal from your assessments. So how to get tricked, how to fool yourself in either research and, well, not research and clinical practice or policy. Believe that every change that you see is because of what you are doing. Believe that if the treatment appears not to work, then it doesn't work, when in fact there could be something else going on preventing the treatment from working. The treatment could be effective if something else was changed alongside it. Believe that everything that you want to be true really is true. You want to think that you're doing good and believe that you couldn't possibly be ineffective. Yes, just blind yourself to the possibility of disconfirmatory evidence and just think that everything you're doing is just fine. Believe that you know everything that's happening with the patient. There could be things going on affecting the outcomes that you don't know about, and believe that if it works here with them, it will work elsewhere with other people. And believe that measurements are always accurate.